Hello. Okay, guys. Welcome to 11 of the reinforcement learning course. So this is the second last live that I'll be doing. So the next Friday. So yeah, the plan today is like go through the contents of what was covered in week 11, and then maybe I'll show a code where you know the learning is implemented. So that could be done in the later half of the class. So we can start. It's already 7:05, 7:06. So I think it's a good time to start. Uh, Screen is visible. I'm audible. The recording is also started. So okay, begin. So uh, different hierarchical works, and in the last list, I have different types of people hierarchical RNs. And last week we discussed two the framework. So today we'll discuss the third framework in hierarchical uh, the RM. So it's not the max framework. Okay. So the method we'll be looking at today known as the value function composition method. So I'll just simply put example that I had used in the lecture. So this is the taxi domain. Yeah. So if you look at the figure over here, it's basically a five. Okay. It's basically a 5x5 grid world, right? And the red boxes here indicates of we cannot traverse. Basically, to navigate this environment, the passengers at one of the locations indicated by B and Y, and then basically did I admit them? Okay. Okay, thank you. So this taximal problem is basically a 5x word problem. So it has four locations where the passengers pop up at random at different time instances, and they have to be picked up at one of these four locations, and they have to be dropped off at the other three locations, right? So the taxi at each time instance needs to navigate, pick up the passengers from the correct location. So it has to execute separate tasks. One is the pickup task, wherein the agent needs to be present at the state where the passenger is also present. And then the pickup task can be executed. Otherwise there is a penalty associated with it. And similarly, if you perform the drop operations at a place where the passenger does not want to get off, then also you actually kind of penalty. So this is the 5x5 grid wall problem. And quickly, we'll just take a look at the max architecture. So uh, this is the max Q architecture. So what you do in this framework is that you basically divide the MDP into small subtasks. So similar to what options uses, also it incorporates the uh, hierarchical abstract machines framework, and uh, combines it both together to make this framework called MaxQ framework. Right? So here you have a root node, which is basically taking care of the execution of the global goal that the agent needs to achieve. In the tactical case, it is that all passengers. So if I have k number of passengers, they need to be dropped off at k different locations. So the root node can be divided into two subtasks: one pickup operator and one is the drop operator. So the pickup operator basically tells me tells me move around, reach to a location where passage is present, and then I can carry out the pickup subtask. Okay, and then you have to divide it further. So the pickup subtask can be also broken down into something known as a navigate subtask. So navigate subtask basically I move around in the grid world without interruption. And the other part is basically pickup. So this pickup is basically a primitive action. So if the initial conditions are met, then the passenger is picked up and you continue navigating. So these are the two subtasks present in uh, pickup sub MDP. And similarly, in the drop of MDP, you have a primitive action which is put down so that if the passenger has reached its desired destination, then it gets down. Then you the put down you similarly carry on similar to the pickup function. And navigate basically is broken down into the four primitive actions, which is go north, east, or west. So this is the framework, MaxQ, the architecture for the MaxQ framework. And so now we will look at the value decomposition, the value function decomposition part, MaxQ framework. So here you have a global MDP, which consists of the set of the global state actions. You have a terminal reward when you reach the, and as architecture is to basically divide the MDP into small subtasks, right? So we have been divided into small subtasks, which are indicated by the index. So this is M1, M0, M1. So this has been divided into K subtasks. Okay, and then each subtask, what it consists of SI. Is basically a set of states that are applicable to my sub MDP MI, and then it consists of a set of actions AI. Again, this actions AI basically corresponds to all the possible actions that I can find in the sub this action is basically can be thought of as a subset of the union of uh, subset of the union of the entire MI times of
Manav,
the
your network is lagging.
okay. And then in addition, you have this RI bar, which refers to in it as the pseudo reward. So this basically tells me that my pseudo reward is the reward that I get on achieving what my subtask tells me to achieve. So if my subtask is basically to go from location G to location B. So if I achieve that sub, there is some reward which uh, will be termed of hello. Am I audible now?
Yeah, you are.
Okay. And my screen is visible also, right?
Yes.
Okay. Okay, fine. So So this is what the MDP, the sub MDP MI consists of. And then the total state space here, the total state space here is, can be subdivided, can be, separated out, make some sort of a dichotomy that it consists of all the terminal states, which I denote by T of I, and then all the states S of I, which are not the terminal states. Okay, so basically all the subtasks are, all the actions in the subtask are, sorry, all the states accessible to the sub MDP's MI is basically the non-terminal state, because at the terminal state, all you need to do is you execute the primitive actions, right? So that's the basic idea. And you move ahead, the max Q value decomposition part. So you have some collection of SMDPs, right? So uh, all these K subtasks can be modeled as a semi-Markov decision process. So if I were to define it mathematically, so this would be states SI, actions AI. And there is a transition probability, which is basically the transitions that I make to states S prime via via state S taking action A in time tau, right? And then I have some reward that I get. I should say the reward I get, which is a function of all these parameters, comma the gamma, right? Gamma is the discount factor. So this is the SMDP that we define. It's a 5 tuple. So on closer look, we can see that this part, so this transition probability part, what it tells me is that once I take a certain action, if it's not if it's not a primitive action, then what I'm doing is I'm invoking another subtask lower in the hierarchy, right? So I'm going down the hierarchy, I'm going down the tree. So I'm invoking another subtask, and that subtask that I'm invoking is basically the action that I've taken. So this can be denoted by this quantity. So what I'm saying is that I'm denoting the AH subtask. So since the actions are, sort of a one hot type of an encoding, or if you encode it into, let's say, your up, down, left, right as 0, 1, 2, 3, 4, and or any other encoding that you make. So all I'm doing is I'm just invoking that particular subtask. I'm invoking the MDP of that particular subtask. And similarly, my rewards are nothing but, as per the earlier definitions, it is the expectations of all the rewards that you get, okay, discounted by the parameter gamma, when the initial conditions that you are in state S and you're taking action A and you're following your policy pi, right? So this is the reward function. This is the entire SMDP modeling that we have done. Now, yeah, so since I'm doing this, so I no longer maybe need my S prime, I no longer need my tau, because I have defined that I'm following my policy pi. So this is a deterministic policy that I'm following. So this is how my reward looks like. And right. So if I were to define my value functions here, so this is the value function for the ith subtask, and when I'm in state S. So when I want to look at the value function, this is basically the expected future rewards given state S, right? So this is basically the immediate reward that I get on executing the policy pi. So this is the first action that I take according to the policy. So the immediate reward that I get plus the summation over all the s prime and tau, all possible transitions that I can, is the probability of the transitions that I make to state s prime when I'm following my policy pi I, okay, times, this is the discounted factor, right? So this is some sort of a recursive, this can be, this can continue recursively until, you reach some, you reach a primitive state wherein you don't have any other, any more hierarchy to go down on, and what you get is the immediate reward, and then that all adds up, right? And similarly, you define your q pi is comma a in similar fashion. So this is my v pi of a of s, right? So even this can be defined as v pi of a of s. The reason being that uh, when I'm following my policy I, whatever action that I take, it is invoking another subtask, and I'm using the value function for that particular subtask. So I'm basically invoking the eighth subtask, right? So this is the immediate reward that you get plus whatever was there earlier. So you have the probabilities of uh, moving to state S prime. So it should be pi I of s times gamma tau v pi of I of s prime, right? So this is how my uh, value function for each state and the q function for each state action pair looks like. Now, if I just were to simplify it, so I can, write this thing as my v pi of a comma s plus my c pi of I comma s comma a. So this is a new term, which is c I comma s comma a, which is basically all the part that comes after the plus sign. So you have okay. So this c pi is known as the completion function, right? So this is saying that once you get in the reward for the action A that you have executed, after that, whatever further actions you take, once the subtask is completed, whatever further rewards that you get, yeah, even when you move to, lower and lower order of subtasks, then all those rewards that are accumulated, sorry, all the rewards that are accumulated uh, are part of this c pi I comma s comma a, right? So this is the completion function, not the completion type. Is the completion function. Okay. So my q value is basically a combination of my v pi a comma s and then my c pi I comma s comma a. Now all I need to do is, if I have a formulation or a terminating condition for this v pi a comma s, then I'm done with my max q framework formulation. Right. So this v pi a comma s is equal to q pi. Okay, this is equal to q pi as pi I comma s. This is applicable if my a is composite. So composite here means not a primitive action. Otherwise, if it's a primitive action, I simply take in the uh, immediate reward that I achieve on completing that action, right? This is expected reward given as a S prime. This is done if A is primitive. Okay. So this is my max Q framework formulation that I have here. Or can also call it as the max Q value function decomposition method. Right. Okay, just last 2-3 minutes I'll spend on this. So my v pi of 0 comma s. Imagine you start at the core. So this is my M0. This is the M0 subtask that I have. So if I want to estimate the value function, so what I'll do is I'll take the uh, the completion function for the 0th MDP plus the value function when I take the first action. So let's say I'm following a policy wherein the actions that I take are A1, A2, A3, and so on. So this is uh, just for nomenclature purposes. This is what we'll be terming as the subsequent actions that we'll take. Okay. So once you do that, so you have this part, and then if you roll this out further, if you go further down, you invoke the A1 subtask. So accordingly, you will have the completion function for the A1 subtask, and then you will take action A2, and then you'll get the corresponding decomposed value function as this. And similarly, if you go ahead, eventually what you'll end up is the summation over all the actions that I took, right? Comma s comma pi I of s. So this is a summation that I have been taking. So it's the sum of all the completion functions that I have accumulated so far, plus basically the terminal reward that you get, right, on encountering the primitive action. So this is nothing but my s prime of b s prime a comma s, and I should be not like this. I'll call it as the R primitive, right? So this is the reward that you get if once you encounter a primitive action, right? So this is how the max Q value function decomposition looks like, right? So yeah, this was all about this framework, and the last part of week 11 basically involved something about option discovery, right? So option discovery is a method wherein you are using the option hierarchical RL framework, and what you're trying to do is essentially there are the problem that you're faced with is basically defining what are like some of the good options that you can make out of the MDP, so that you can have faster learning or a better learning, right? So sometimes what happens is the options that people come up with, they are sort of sparse, right? And they are very hard to discover. So uh, similar to the example that Sir used. So if you have a two-room kind of a setup, so you have two doors, right? So if I want to move from room A to room B, I need to culminate at, or I need to come up at one of these two doors, and only then I can move into room B. Otherwise, all the explorations that I make are some sort of a random exploration that I have been doing, right? So the advantages of this option discovery is that uh, this helps in reusability. Second is this cuts down on exploration. Because if you discover these options, you don't need to explore any further. So this helps in cutting down on exploration. And third thing is that it also aids in transfer learning, right? So you can think of these options as something known as bottlenecks, right? So bottlenecks are basically the set of good states or good options that helps you pass from from one sub MDP to another sub MDP or yeah. So these bottlenecks something are some sort of a desirable state that we need to discover more and more. So this is what option discovery is all about. So the way in which you can utilize or make use of this bottlenecks, sir has mentioned different methodologies. So one method is by means of graph partitioning, right? So what you do in graph partitioning is that you basically segment. What you're doing is you segment the MDP, in, segment the MDP into small graph components, and then what you're doing is then you are finding, and then what you do is you find uh, sorry, you find the graph components that are weakly connected. So these weakly connected graph components indicates a bottleneck in the figure, right? So if there is a distinct partition between graph into two components, and there are some states which have a weak connection, then those states are known as bottlenecks. So if you look in the domain of network analysis, that's what we mean by bottleneck. So let's say you have some graph which are connected in this manner, and then there is another, or rather I should say subgraph. So they are very densely connected, but between these two states, there is a very weak connection. So it's almost separated out, but some weak connection is there. So if you find these kind of graph components, then so these are indicative of a bottleneck in the MDP that you have, right? So this is one method. Another method is by means of diverse density. Okay. So what happens in diverse density is that you assume that you have a lot of trajectories that you have generated, right? So a lot of generated trajectories that you have stored in an experience replay buffer. So a lot of trajectories are successful because they end up in the goal state, and a lot of trajectories are unsuccessful. So what you do is you do some sort of a statistical evaluation on these set of trajectories. So first thing is that you assume you have lots of generated trajectories, and then what you are basically looking at is the number of states that appear in successful trajectories and not in unsuccessful trajectories, right? So again, this is an indication of a bottleneck being present in the state. So if you have a lot of different trajectories, randomly generated trajectories, so there are certain states which keeps on appearing in successful trajectories, and there are some states which don't appear. I should write unsuccessful. Yeah. And some trajectories which don't which appear do not appear in any unsuccessful trajectories. So that is again an indication of a bottleneck. So this type of methodology is known as diverse density methodology. So this is again some sort of a heuristics that people use. in figuring this out. The third thing is something known as betweenness centrality. So if you're familiar with the you know graph theory or network theory or network analysis part, so what betweenness centrality indicates is that it's basically a centrality measure for a node. So a node has different centralities. It has degree centrality, it has betweenness centrality, and different centralities. So so here a node has a high betweenness centrality if lot of successful or a lot of shortest paths pass through it. Shortest path pass through it. Right. So this is the what betweenness centrality tells me. So if there are multiple shortest paths that you have from getting from location A to location B, so a node has a high betweenness centrality if a lot of the shortest path pass through that node, then the betweenness score is high. So there is a very strong correlation, right? So it has a very strong correlation uh, between or strong correlation in betweenness in the betweenness centrality and bottleneck. So this is a good indication or a direct evidence that a high value of betweenness centrality indicates the existence of a bottleneck in that particular graph, right? And then last one is the small world MDP, small world MDP setup, right? So here, what you're trying to do is you convert your MDP into small world MDPs. So a small world MDP indicates that you can reach from your start to the goal position in a very few number of steps. So that is the definition of a small world MDP. And then from that small world MDP, you basically define or partition it into your small world graphs. And then turns out that this small world graphs, helps in cutting down on exploration. And then what you're trying to do is you basically draw out random trajectories on these small world graphs, and then you use that to define useful options out of it, right? So again, this is one method for option discovery. So these are the 4 different points that Sir had mentioned in his lectures for regards to option discovery, right? So yeah, I think that's all I had in mind. Maybe we can look at a code uh, for options Q learning. Maybe that could we can just look at the code. Right? Yeah, so I'll put the link here. Also, is my screen visible?
Yes, it is.
Okay. Yeah. So this is a code block that is there. Just to give an introduction to the implementation for options. So I won't execute the code because the results are already generated. So I'll just quickly run through the code and you can look at it. Right? So these are the bunch of imports that you have. And then this is here what you're using is a very naive example. Okay, so here you don't necessarily need options to do the learning, but this is a very naive example. So the environment that we are using is the cliff walking example, right? So you want to go from one point to the other point. In between there is a cliff. So the example that we had seen in when we were doing the comparison between Q-learning and Sarsa. Okay, so this is a gym environment known as cliff walking environment. So you define that environment, you call the reset part, and then you print, right? So env.s basically prints the state that the agent is currently at. So since this is a 4x12 grid, so there are total 48 number of states. If I do print number of states, I get 48, which is over here. And then the primitive actions that I have are up, right, down, left. They correspond to 0, 1, 2, 3. That's actually passed to the environment. So these actions up, right, left, down is actually 0, 1, 2, 3. And then the number of actions that an agent can take is basically 4. Okay, so this is env.n of a. This is number of actions. And then some example transition. So here I'm choosing a random variable between 0 and 3. So this is a random action. Then I print basically the action that I have taken. Then if I do env.step on that random action, I get the next state reward if it's terminal and the probability of taking that action. Okay, so this is what it prints. So because I am at state 36, right? So initially I am at state 36. So 36 indicates this part, right? So if you start counting from 0, 1, 2, 3, so this is still 11. So this is from 12 to 23, 24 to 35. So this is from 36 to 47, right? So my goal is to go from state 36 to a terminal state, which is at 47. So the random action that the agent here takes, if I just sample it, it's to go right. So if I go right, I fall into the cliff, right? So the transition probability is 100, 100% probability I go to this. So there is no, uh, stochasticity in the action that I'm taking. And because I fell into the cliff, the next state that I will turn up is again in state 36 because the episode terminates and I start up with a new episode. And the reward I receive is minus 100, right? So if I fall into a cliff, I get a reward of minus 100. Otherwise, at every other stages, I get a reward of -1 until I reach the goal. So here we custom define very simple options here. They might not be the logical options for this setting. Deliberately chosen to visualize the Q table better. Okay, so here we are defining two more options, right? So one option is away. So away means that I'm moving away from the cliff. So what this option tells me is that you just keep going up. And then option 2 basically tells me that close to cliff. So keep going down. So this is the two functions that I have defined here. So this away environment basically tells me that option done is always false. Option act is 0. So 0 means to go up, right? If int state divided by 12 double equal to 0, then my opt done is true. And then I return opt act and opt done. So what this tells me is that because okay. So what this tells me, so what this if condition tells me is that I continue to continue to use the away option. So I continue to move up until my opt done is true. So my opt done becomes true when my state divided by 12 equal to 0. So because this is an integer division, so any state, the state value, anything that the state value has less than 11, less than 12, then my opt done is true. So what this indicates is that I am at the upper row. So this is state 0, 1, 2, 3 till 11. So if I'm at any of these states, so my state divided by 12 is equal to 0. So that means I can't, I no longer can go further up. So this is like the beta for the option, right? So my beta is true here. And then similarly in the close part, so the action that I take is 2. 2 means to go down. And then if my int state is equal to 2 or is equal to 3. So this is corresponding to either the third row or the fourth row. So if I'm at any of these two rows, not in the cliff, of course. If I am at the cliff, then the episode terminates. So the fourth row just contains two states. If I'm at any of these two states, then my opt done is true. So now the new action space will contain your primitive actions, which is up, right, down, left, and then the two options away and close, which you define. So the total number of actions is up, right, down, left, away and close, and they correspond to 0, 1, 2, 3, 4, 5. Right. So now we'll define the Q table for the SMDP. So I define Q value as SMDP. So this is np.0 is 48,6. So because I have 48 states, so because I have 12 cross 4 states, and then the total number of actions is 6, right? And then this is the frequency data structure. So I define this step MDP. So step MDP basically means how many times I encounter that particular state action pair. Okay. And then this is the epsilon greedy selection policy. So if I basically select a random number between 0 and 1, if this is greater than epsilon, I take np.argmax. Otherwise, I do np.random.choice. Right. And yeah, so this is the Q learning algorithm. So the parameters that I'm using is my gamma is 0.9, my alpha is 0.001. So my alpha is basically what is a step size parameter, right? So I iterate over 1,000 episodes. I do env.reset. This is my initial state. My done is false. When episode is not over, while not done, I choose action in an epsilon greedy fashion. Whatever state action pair that I encounter, I just update the step part. So this is just taking a note of the frequency with which I visit that particular state. And then I check if it's a primitive action. So if action is less than 4, so if the action is 0, 1, 2, 3, I perform my regular Q learning update for the state action pair. So this is the env.step action. And then whatever, this is the Q learning update for that particular state action pair. So this is the SMDP Q learning part, right? And then checking if the action chosen is an option, right? So my reward bar, so my R bar is 0, my G is 1, my start state is S. If my action is 4, so if the action is the away action, I start with opt done is false. And while opt done is false, so I'm just, I continue to, so while opt done is false, I execute that particular action, do the update. I update my reward bar. So this is G plus the reward. And then I do G multiply equal to gamma. So this is G is basically the gamma part for this reward bar. So this reward bar is RT plus gamma, RT plus 1, and so on uh, that we had seen 10, 15 minutes ago, right? And then I do state is next state, and then finally I update all the Q values based on the reward bar, not on the reward, right? And then if the action is 5, I do the same thing, and the update is as follows. So this is my standard SMDP Q learning. Okay, so this is the function for that. Similarly, we'll look at the SMDP Q learning for intra-option part. Okay, so here in whenever I encountered any option, so I'm just taking in the reward, doing the discount and adding it, right? So I'm not performing any Q learning on the options as such, right? So here in intra option Q learning, I'll also be performing Q learning on the options as well, right? So similar to what we had defined above. So we have the gamma, the alpha. So checking if primitive action is less than 4, you perform your regular Q learning update for the state action pair. And then if it's an away action, so I'll perform Q learning on that part as well. So I'm doing a Q update for each action or each for each of the actions that I'm executing when I'm in that away option part, right? Okay, yeah. So I keep doing that. And similarly, this is for the close option, right? So now what we're doing is we'll just compare the two Q tables and the update frequencies and provide some comment, right? So this is the table for the inter-option Q learning. So this corresponds to my 48 states, and these are my 6 actions, right? So what the first thing tells me is basically it gives me the heat map of the Q values for the intra Q learning, right? So what you see here is that whenever I am at state 36, I am always required to take the up action, right? So that is getting highlighted here. And then otherwise, at any other, when I'm at this, when I'm at state 36, I'm always taking the up action. Rest of the states haven't been visited sufficiently enough to make any sort of conclusion. And then this indicates the third row, right? So this indicates the number of times I'm in the third row. So if I'm in the third row, I tend to move to the right. So 2 indicates the action corresponding to moving to the right. And then the option here is uh, this is the close option. So I need to come closer and closer. So this is my second row. This is my third row. So this is how this looks like in intra-option Q learning. And again, this is the frequency, right, that we have seen. The frequency at which each action is, each of this thing is encountered, right? And similarly, I think similar results you can see here in the SMDPQ learning. I think it's more or less similar, except that you have access. You're also moving. You also have explored the first row here as well, right? So because the cliff walking environment is not really an SMDP kind of a model, just a naive example. This can very well be modeled and solved as a normal MDP problem, but just for an introduction to options. So this is how it looks like. And then here what we observed is that in intra-Q learning, the table states 0 and 10, which is the first action. And the options 5 has values close to -5, but in SMDP Q table states, the action 5, which is the close options, has high negative values. This seems to justify that the close action in SMDP leads to much more negative values. So this part, right? So this was the only difference that we observed, and this is the conclusion that you draw from this, right? So I think, yeah, that's all I had for today. I think I'm done on whatever I wanted to present. If you have any questions, you may ask. Otherwise, I've completed what I wanted to cover for today.
Thank you, Manav.
Okay, then. Thank you. Thank you for joining. I'll see you in the next class, which will be my last class for this course. So
Yeah, sure,
bye.
sure.
Thank you. Have a nice day.
Yeah, you too. Take care.
Bye bye.